Okay, in this presentation I want to focus more on some of the basic science involved in homocysteine and the various players in these pathways that are relevant to homocysteinemia. And my goal is that at the end the viewer will have an appreciation for why deficiency in folic acid, vitamin B12, and vitamin B6 affects homocysteine metabolism, to of course understand how homocysteine is used in the production of cysteine, to understand how the enzyme methylene tetrahydrofolate reductase, MTHFR, is relevant in homocysteine metabolism. And finally, we'll touch on the enzyme cystathione beta synthase, deficiency in which is the cause of homocysteinuria. So here we have our main player, homocysteine, sitting in the middle of the diagram. And the first thing to understand is that homocysteine is an intermediate that's used ultimately in the production of cysteine. So this is the goal, is to produce cysteine. And the cysteine is being produced from the amino acid methionine. So again, we start with the amino acid methionine and produce cysteine. And the production occurs via several steps. One of the key intermediates is homocysteine. The diagram that you're viewing now is a modified diagram from a figure taken from Nature Reviews, from an excellent review article that provides information on homocysteine metabolism in much greater depth than that which I'll deal with in this presentation. Let's take a look at these amino acids here on the side to get a better understanding of what we're looking at in terms of structure. We start with cysteine over here, which is what we're trying to achieve. And we see that it has a rather simple side chain composed of one methyl group and attached to a thiol group, the SH group. What we start off with, the methionine has those components. We have the methyl group and the thiol group. However, we have some unwanted methyl groups that we need to take off. And we see that homocysteine is an intermediate in which one of those methyl groups has been removed, the one that was on the extreme end. But we're still left with one methyl group that needs to be taken off. So we hopefully now understand how what we're going to do is that methionine is converted through this pathway here involving an enzyme called methyltransferase, which obviously it makes sense that it removes one of the methyl groups off to bring us to homocysteine. And then homocysteine can then be converted through two enzymes to cysteine. And these two enzymes are cystathione beta synthase and cystathione gamma lysase. So what happens is that homocysteine is first converted into this entity called cystathione. Cystathione is an interesting molecule where it's basically two amino acids linked at their side chains, and those two amino acids are homocysteine and serine, which we see comes in here, and we'll show an illustration of cystathione in a moment of how these two amino acids combine. And then this entity is then lysed to leave over cysteine. So here we see homocysteine in a slightly different orientation, where we have the side chain composed of the two methyl groups attached to the sulfur, or the thiol group. And in this reaction, cystathione beta synthase combines it with serine, the amino acid serine. Here's serine side chain, a methyl group and a hydroxyl group. And through the reaction, which involves the removal of a water molecule, the two link together, as we see over here, to form cystathione. And then the next step is that the enzyme cystathione gamma lysase cleaves this molecule here to provide cysteine here, where again you have the side chain of the methyl group attached to the thiol group. Coming back to our original diagram, what's important to point out is that the activity of cystathione beta synthase requires the cofactor of vitamin B6, and so we understand now how a deficiency in vitamin B6, for example, will likely contribute to homocysteinemia, a failure of the ability to convert homocysteine into cysteine. So what's important to point out that while homocysteine tends to be converted into cysteine, it can also be, and is to a certain extent, recycled back into methionine. And so the prevention of elevated levels of homocysteine is mediated not only by its conversion into cysteine, but by its conversion back into methionine. And deficiencies in the components that are responsible for the reconversion to methionine can also lead to elevated levels of homocysteine. And two important players that we need to focus on in terms of the conversion of homocysteine into methionine are vitamin B12 and this substrate that's called methyl tetrahydrofolate. So we can appreciate, first of all, that vitamin B12 is a cofactor that's used in the conversion of homocysteine back into methionine, and therefore a vitamin B12 deficiency will contribute to homocysteinemia. Furthermore, a lack of this compound, methyl tetrahydrofolate, will also prevent the conversion of homocysteine back into methionine and also contribute to homocysteinemia. The production of methyl tetrahydrofolate is mediated by this enzyme here, MTHFR, which has received much attention over the years because of various mutations that exist in the population that compromise its ability. The full name of the enzyme is methylene tetrahydrofolate reductase, and that's because it acts on this molecule here, methylene tetrahydrofolate, and converts it into methyl tetrahydrofolate. So from methylene to methyl, and we'll show the enzymatic reaction in a bit. And so that if this enzyme is not working properly, we will have a reduction in the amount of available methyl tetrahydrofolate, and this will lead to a compromise in the ability to convert homocysteine into methionine, and therefore lead to elevated levels of homocysteine in the plasma. Okay, so now we come to discuss folic acid. Folic acid is critical for this cycle here. And we know that folic acid is a very important element of our diet. Pregnancy particularly, it's extremely important. And that's because of the many things that are dependent upon folic acid, such as the production of purines, such as adenine and guanine, which are essential for the formation of nucleic acid and DNA, which will be very important in a growing baby during the pregnancy. And it's also very important in terms of the production of the amino acid cysteine. So how does it work? So we've already alluded to the necessity of having methylene tetrahydrofolic acid, and this is obtained from folic acid. So folic acid is obtained from the diet. It's converted by this enzyme, dihydrofolate reductase, into tetrahydrofolate or tetrahydrofolic acid. We'll see that now in an enzyme reaction. So here's the specific enzyme reaction that takes us, converts folic acid into tetrahydrofolic acid. And this is at the expense of an NADPH, where this enzyme dihydrofolate reductase reduces folic acid By reduction, we mean the insertion of a hydrogen to produce this molecule here, tetrahydrofolic acid. And so once tetrahydrofolate is produced, it can then be converted into methylene tetrahydrofolate, which can then be converted into methyl tetrahydrofolate by the enzyme MTHFR. In this reaction, we see the enzymatic activity of MTHFR converting methylene tetrahydrofolate into methyl tetrahydrofolate, a reduction involving the addition of a hydrogen into this area of the molecule here, again at the expense of an NADPH. So hopefully now, as we wrap up this mini presentation, we can see all the major players that will affect the levels of homocysteine. We see that in order to metabolize homocysteine, we need this enzyme here, cystathione beta synthase, and a deficiency in functional cystathione beta synthase is what causes a different condition, homocysteinuria, which is a very severe condition which causes not only elevated homocysteine in the plasma, but actually excretion of homocysteine in the urine. And we'll discuss that later in a different presentation. And we need, for the same process, vitamin B6 to be present. We need vitamin B12 to be present as a cofactor in order to convert homocysteine back into methionine. And that same enzymatic reaction requires the presence of this molecule, methyl tetrahydrofolate, and the production of that molecule is dependent upon this enzyme, methylene tetrahydrofolate reductase, and that this is an enzyme in which it's very common in humans to have mutations which compromise the ability of this enzyme to function. And a compromise will obviously therefore compromise the ability to metabolize homocysteine back into methionine and contribute to elevated levels of homocysteine. And finally, we see the importance of folic acid, how if we have a deficiency in folic acid, that will obviously translate into a deficiency in methyl tetrahydrofolate, and therefore a deficiency in the ability again to metabolize homocysteine back into methionine, and therefore lead to elevated levels of homocysteine.